we've been talking about all these applications that's built on the blockchain. But what exactly is the blockchain and how does the technology work? Now, the easiest way to think about this is the blockchain is just a ledger. Now, what's a ledger? Well, let's say that I went to lunch with my friend Jack and he paid for the bill. Well, I could pull out a notepad and say, well, Jack gave Angela $10 for lunch and now Angela owes Jack $10. So this is the beginning of my ledger. Now, then I decide to buy Helena a coffee, so Angela gives Helena $5. And as I continue this ledger, it's basically just a record of who owes who, what amount, and just a bunch of data. Now, later on, when I want to figure out, well, how much do I owe Jack? Then I can look at this ledger and I can see, oh, I owe him $10. But there are two problems. First, Jack, Helena, and I all need to agree on which transactions should go into the ledger. And second, we have to trust the person who's holding onto the ledger, that they aren't just going to modify the transactions that we already recorded. What if we could just simply modify this ledger? I could just go in there and add a 0, and now all of a sudden I'm receiving $100 instead of $10. This kind of data tampering makes these kind of paper ledgers worthless to use, and if we had this on the internet, it would have the same problems. What we need is to make the history of the transactions in this ledger immutable. Basically, lock it so it can no longer be changed ever again. How do we do that? Well, we could do that with encryption. And the simplest version is the Caesar cipher. So when Julius Caesar wanted to communicate with his generals and wanted to make sure that the messages didn't get intercepted by a third party, he turned his message into a cipher. That means if somebody got hold of it, they wouldn't be able to work it out unless they knew how it was encrypted. And this was a very simple form of encryption. All it did was it shifted the letters in the message by a pre-specified number of characters. So maybe A becomes E and B becomes F, etc. Now, if you wanted to try out the Caesar cipher for yourself, you can take a look at this Caesar cipher demo, which I'll link to in the course resources. Now here you can enter some plain text, and if you click on encrypt, you can see that there's a shift amount. So what it's going to do is it's going to take each and every letter and shift it up by 4. So an E becomes an I, a L becomes a P, etc. But you can see from looking at the ciphertext that there is a pattern here, right? Because with the double L's, it's 2 P's, and then with both of these U's in Julius, they both get encoded to Y. And if you knew which cipher was being used, you could just go through all of the shifts, from 1 to 26, and you'll eventually figure out how to decrypt this message. So if you click decrypt, you can see it goes back to hello Julius. Now, the only thing that you need to know is what that shift number is in order to figure out how to decrypt a message. So here they've got an example message, and if you try decrypt, you can see it's still not working, and you change the shift number from 1 to 2 to 3 until eventually you'll get to the right shift number and you'll figure out what the message is. Try it out yourself. The Caesar cipher is one means of encryption, but there are many, many different types of encryption. But what they all do is they take a message and you encrypt it and you can turn it into a cipher, which will be difficult to read for any normal human being, and you disguise the meaning of the message. Now, the key thing about encryption, though, is that you can actually go forwards and backwards, which means that you can take the same encryption. As long as you know the components of the encryption, you can decipher it and get the message back out. So this means on the other side, the Roman general will be able to read what Julius Caesar meant to send him by knowing which form of encryption was used. And this makes encryption a little bit less secure, because if there is a method to be able to back out the original data by decrypting the cipher, then your cipher could be broken, such as in the case of the famous encryption of the German Enigma in World War II. So if our ledger was secured using encryption, then there's always a way to decrypt it, which means we can still alter the ledger illicitly. So instead of using encryption, the blockchain actually uses something called hashing, which is very similar to encryption with a couple of notable differences. Now, what's hashing? Well, it's basically a mathematical formula that allows you to turn a message into a hash code by passing the message through the hash function. But unlike encryption, a hash is a bunch of mumbo jumbo, but if you use the same hash function, no matter what message you put in, you will always get an output with the same number of characters. So if you hashed 123, you might get this top result, and if you hashed ABC, you might get this bottom result, but they both have the same number of characters. So let's try out a hash algorithm ourselves. Now again, in the course resources, you'll see a link to this demo. And here we've got the SHA-256 hash algorithm, which is one of the most popular hash algorithms out there. And you can see here that you can type any sort of message into this box and it will formulate a hash. And it changes every single time you type anything. So you can type a space, it'll change it. You can type numbers, it'll change it. You can put the entire War and Peace into this message box and it will still generate a hash with 64 characters. And if you're interested, you can actually see below here for the source code of how the SHA-256 is implemented. But how is it possible that we can turn an input into a hash and be completely unable to work out what the original input is from the hash? Well, a really simplified example of a hash function is working out the factors of a number. For example, 2 times 4 is 8, so 2 and 4 are the factors of 8, because I can divide 8 by 4 and it will cleanly divide, and I can divide 8 by 2 and it will also cleanly divide with no remainder. So going forwards is very easy. 2 times 4 is 8, super easy. Now, if I asked you to work out what are the factors of 8, which would be 1, 2, 4, and 8, that's a little bit more difficult. But what if I asked you to work out the factors of 57? Unless you already know what they are, you have to go through all the numbers. So it will be 57 divided by 2, 57 divided by 3. Now here you would find that 57's factors are 3 and 19, because it can be cleanly divided into 3 and into 19. But what if I asked you, are there any other ones? Well, you can't be sure unless you actually continued. So you could say 57 divided by 4, that doesn't cleanly divide because there's a remainder. Then you do 57 divided by 5, and so on and so forth. So essentially, when we're multiplying 2 numbers together, it's almost like creating the hash from the message. And then the final result that we get is the hash. But if you wanted to go from the hash to go back to the original message, you would have to brute force it. You would have to divide it by every single number from 1 to 57 to find out all of its factors, which for humans takes a lot of time and for computers takes a lot of energy and computing power, especially when you're dealing with very, very large numbers. You already saw how finding the factors of 57 was a lot more difficult than finding the factors of 8. Now, real-world cryptography uses numbers that are hundreds of digits long. For example, in 2019, it took researchers 900 years of computing power to find the factors of a number with 240 digits. So this is kind of the underlying basis of cryptography. Going forwards is very quick and easy, very easy to calculate, but going backwards is almost impossible using the current computation power that most people have access to. So how does this apply to blockchain anyways? Remember that our problem with the ledger was that we wanted to make sure that no one can change our history of transactions. Let me show you how the Bitcoin ledger solves this problem. Using what we know about one-way functions, we can now take our transaction data and create a hash. Some very clever people have figured out that you can encode a whole bunch of things and hash everything together. So for example, I could write a message and I could write which date it was written on. So the 1st of January of 2023. And I could also say, I am the person who wrote it. My name is Angela. I could put all of these information together and it will create a hash for me. So this is essentially how a block in the blockchain is formed. We have a piece of data. So let's say Angela owes Jack $10. This is our piece of information. This is our piece of data that we want to encode into a block. Now, in order to add that into the block, we're going to have to generate a hash. And the hash becomes the identifier for this block. It's kind of like the fingerprint of this block. How can you know that this block is truly this block? Well, you could look at my fingerprint and it's probably different from yours because we are unique people. And you can look at this block and it'll probably be different from another block because it'll have a different hash. Now, in order for a block to be added to the blockchain, it has to satisfy some predetermined requirement. And this requirement could be, for example, that the hash has to start out with 3 zeros. Now, you can see that as I start typing, the hash keeps on changing. And sometimes you might see that we get just purely by chance a 0 to show up, or in this case, even better, 2 zeros to show up. But if we wanted a hash that has to begin with 3 zeros, then we're going to have to keep modifying our data, which is not what we want. We want our data to be clean. Or we can modify this thing, which is known as the nonce. So the nonce is basically a number. So we can start from 1 and you can see the hash change because the nonce is being combined with the data to produce the hash. Now, 1 produces a hash that starts with 4, so that doesn't work. Well, 2, we can try 3, we can try 4, we can try 5, and we can keep going through these numbers until we find a nonce that creates a hash that starts with a 0. But that's not enough for our block to be added to the chain. We need it to be 3 zeros to begin with. So you can continue changing this nonce to 7, to 8, to 9, until quite a while, trust me, I've tried it, to find a hash that begins with 3 zeros. Or you can simply use the computer and do that for you to brute force the nonce until it finds from 1 all the way up, increasing by 1 each time until it finds the right number that's going to create a hash with 3 zeros. And you can do that by simply clicking on the mine button in this website. It took 0.1 seconds for my browser to figure it out, and it figured out that 3,885 is the nonce that I need in order to encode this data to have a hash with 3 zeros to start with. So this makes this block valid, and you can see it turned green because it satisfies the requirements of the blockchain to have 3 zeros to begin with. Now, if I had a blockchain that had a little bit higher of a difficulty, well, I can change that to 4 zeros to start with, or 5 zeros to start with. So then it's going to have to iterate through all the nonces until it finds a number. When combined with this particular piece of data, will produce a hash with 5 zeros to start with. And you can see when I click mine, it's going to take a little bit longer, 0.6 seconds, before it finds the correct nonce, which happens to be 53,792. But the important thing is that nonce only works to produce this hash with 5 zeros for this piece of data. As soon as I alter this piece of data, let's say that Jack decided that I actually owed him a bit more money, and he goes in and sneakily alters this data, well, it's now become invalid because you can see the hash no longer starts with 5 zeros. And this tells me that this block has been modified and it is not valid data. So then what we're doing with our ledger is we're taking the data that we want to add into the ledger and we're putting it into each of these blocks. by hashing the data with a nonce. So this is where the block in the blockchain comes from. But what about the chain part? So if we go to the next tab of this demo, you can see we've got a whole bunch of blocks here, 5 in total. And each of the blocks, in order to create the hash, it takes into account the hash of the previous block. This is how they're chained together. So here you'll see that the hash of the first block, which is called the Genesis block, because it doesn't really have any previous blocks attached to it. So that's just 64 zeros in this case. Well, this has a hash though. And let's say that we decided to put in the data that Angela owes Jack $10. Now, in order for this block to be valid, it needs to have a nonce that combines the data with the previous hash value, which in this case is 0, to create a hash that starts with 5 zeros. So we can click mine and we can get our computer to work it out. There it's found the nonce 53792, and with this nonce and our data and the previous hash, all of these things combined creates a hash with 5 zeros to begin with. So this is now a valid block that's entered the chain. Now on the next block, let's say that I decide to give Jenny $5 and I want to record this into my blockchain ledger. There's my data. And now you can see this is going to be chained to the previous block because it's now got the previous block's hash in this section. And this plus this plus this is going to be combined to create this hash. When any of these things changes, so for example, if I change the data, if I change the nonce, and I can't, but if I did change the previous hash, it will also change the hash here. So these three things together create the hash. Now, if I go ahead and mine it, you can see it'll figure out a nonce in order to satisfy my requirement, which is 5 zeros to begin with. Now, here's the interesting part. If I decide to go back in time and alter something in the ledger, so let's say that instead of me owing Jack $10, I decide to sneakily change it to Jack actually owes me $10. You can see what it's done is it's invalidated not only this block, it's turned it red because it doesn't start with a 0. It's also invalidated every subsequent block. So because this block depends on this one, and the previous hash function has changed, which means this has changed, and because we said that these three things together create the final hash, it no longer starts with 5 zeros. So this means I can't change this data without people knowing about it. And if I change the data back to the original form, you can see everything turns green because that is the original state of the ledger. And this is how the ledger stays immutable. We can't change anything that goes into the blockchain. Otherwise, it's going to invalidate all of our hashes and it's no longer going to satisfy the requirements. So as you can imagine, if you had more data and you mine each piece of data until you have this entire chain, which is all linked to each other, because in order to create each block's hash, it takes into account the previous block's hash, and whenever the previous block's data changes, it's going to change the hash and thus invalidate every subsequent block. Then this is how we can have security in our blockchain. We now have a ledger where every single time you change anything in a previous block, it's going to invalidate every subsequent block. And in order to make it valid, we have to remine every single one of these blocks, which, depending on the difficulty level, I haven't even set it that high, is going to take a lot of time because we're going to have to go through each of them. And in reality, in chains like Bitcoin or Ethereum, it would literally be impossible with the current computation power to be able to go through each of the blocks and remine them. And you can see, even in this case, which is a very simple one, my Chrome is already telling me that it's hanging and it's not working and I should shut it down. So this is how we ensure the integrity of the blockchain. But blockchain actually goes even one step further in order to assure that the data that's stored is absolutely correct and has not been tampered with. And this is the distributed part of the blockchain. This goes back to the first problem that we talked about. How does Jack, Helena, and I all agree on what's in the ledger? So I'm going to make this a little bit easier on my computer and drop the requirement to only need 4 zeros. So you can see here I've got a distributed blockchain. So I've got 3 people with 3 computers, peer A, peer B, and peer C. And what happens is every time a new miner joins the blockchain, they're going to get a full copy of the blockchain. So this person's blockchain has the same data as this person's blockchain. And you can see, because if you look at the hash, they're all completely identical. So now what this means is that 3 people have the same blockchain that they hold. Now, if this first person, peer A, decides, oh, I'm going to be a little bit cheeky and I'm going to change the data in here, I'm going to say that, in this block, actually something else happened, then you can see that they've invalidated all of their subsequent blocks. Now, they could remine each of these blocks in order to make it valid again. Now, because I've set the difficulty quite low, that was relatively quick to do. But now they no longer match up with the other blocks. You can see this one starts with 4 zeros, but then it's 347E. But for the other 2, they've got A88F, A88F. And this is how the network can tell that this peer A has become a bad player. They're trying to mess with the system because their hashes don't match with anybody else's. So by distributing the blockchain on multiple computers, we now have another way of ensuring the integrity of our data to make sure that our data is absolutely correct and nobody has tampered with it. And this is where the power of blockchain really comes in, because we now have a distributed, trustless ledger. We don't have to trust anybody. We don't have to believe that, PayPal is storing my money and they are making sure that all the transactions are correct. Well, actually, we've got blockchain, which encodes all of these transactions. And because of the underlying technology, the distributed nature of it, the blockchain part, it means that we don't have to care who is storing these copies of the blockchain. We can trust in the technology, that our ledger is always going to be accurate and nobody is going to be able to tamper with it. Now, this is great, and this technology up to this point that we've described already allows us to have cryptocurrencies like Bitcoin. But the real cherry on top happened when Ethereum was conceptualized. Now, the real breakthrough here is they realized that not only can we store data inside each of these blocks, who owes who money or who has how much money, we can create what's called smart contracts by storing code into the blocks. So back in our blockchain demo, we could have code. For example, if we were running a Kickstarter or a crowdfunding type of Web3 decentralized application, then we could have the code that says, well, if the total amount was greater than, whatever goal they set, so maybe $5,000, well, then in that case, this code is going to execute and we're going to transfer the money. So let's say Angela has an account and it's going to get these $5,000. We're going to increase Angela's account by 5,000. So this code then gets put into the block, which is going to create our hash, which means that it can never be changed again. And then a user can come along and execute this code, and the resulting transaction where Angela gets $5,000 will get saved onto the Ethereum blockchain. So now, instead of having a crowdfunding company like Kickstarter, who's going to escrow the funds or who's going to make sure that, the money, once the goal is hit, gets transferred to the project owner, well, we've actually got all of that encapsulated in a few lines of code. So when somebody decides to raise some money and they happen to reach their goal, then our code from the block gets activated automatically and transfers the money to the recipient. And this is where the real mind-blowing part of blockchain comes in. And that is exactly what we're going to learn in this module: how to create these decentralized applications and getting our apps to do things automatically based on the code that's stored on the blockchain.